as this can bring in sediment and create issues when trying to clean out the tip and pouring the shaft. Like I said, the most common installation approach for setting permanent casing is to use the telescoping casing method. And this just simply involves exactly what it sounds like. You're setting an oversized casing into the ground. Say, for example, if you have a 5-foot diameter permanent casing, then you're going to install a 6-foot diameter or greater temporary casing into the ground. And then if it's slurry method, you fill the hole with slurry, but we'll go through that in a second. But for generally telescoping it down, you're going to set it to a point at which you can start drilling out the stratum in a way that it can remain stable, and then you're going to go and set your permanent casing. Another very common, especially on the West Coast and around sensitive structures, casing installation approach is casing install ahead of excavation. This is seen a lot on railroad projects because you're generally drilling under an active bridge and right up against existing deep foundation elements. Or if you're drilling in high seismic zones, somewhat out west with liquefiable soils, it's a very common practice as well. And it involves using an oscillator, rotator, or drill rig. And you have to take the casing down, leaving a soil plug, and drill out as you're advancing the casing. And the key there is to never get your drill tool below the point of the casing advancement. A fairly old school way and pretty simplistic method, permanent casing installation, is by vibrating it in. It's a really great approach. Typically, it's reserved for greenfield sites where you don't have any structures around you. Some of the risks, as I just said, are vibrating casing in if you have sensitive structures or a sensitive site where vibrations can be problematic, or if you've got very dense ground or there are known obstructions. As vibrating a casing in, you can't exactly vibrate it through obstructions, whereas with a drill rig and advancing a casing, you have the ability to go down and deal with obstructions a lot more readily. The last type of casing installation we'll run through is the sectional casing. And sectional casing is double wall, inch and a half thick casing with a starter shoe, and then you've got sections of casing you can bolt together. This is a great method for installing at shallower depths. Typically, depending on the diameter, you're going to limit out the ability of a drill rig to install sectional casing at around 75 feet. If it's small enough in diameter, you can go excess of 100 feet. But really anything greater than that, you've got to start utilizing something like an oscillator or a rotator. The advantage with sectional casing too is you can extract it after you pour. So you can use it in both situations of just needing temporary casing or using permanent casing. In the sense of permanent casing, you would just set a larger diameter sectional casing, drop your permanent casing into the hole, and then extract your sectional casing. So there's two main types of drill shaft installation. There's the dry method and the wet method. The dry method is exactly what it sounds like. You're drilling in dry conditions. You're not dealing with groundwater. It's the ideal approach to installing a shaft just because there are less problems in drilling in dry conditions. You don't typically deal with caving ground conditions. So usually it's in areas where there's significant clay layers, or if there's a cohesionless layer, it can be sealed off above it, sealed off until you get down top of rock with the casing and you can drill an open hole. But again, it's only allowed under certain conditions. Typically, a hole is considered dry when you have less than 1 inch of water infiltrating in 5 minutes or 12 inches of water infiltrating in 1 hour. In dry hole condition, the ideal concrete placement is going to be through free fall. Again, in order to free fall, you've got to have less than 12 inches of water inflow per hour. Anything more than that is going to be excessive, and you're going to have to switch to a trimming method. One thing I'll say about free-falling concrete is the industry at this point is fairly disjointed in who allows free fall of concrete. The DOTs, depending state to state, we've seen DOTs that allow free fall concrete around 5 and 10 feet max, and we've had DOTs that allow free fall of concrete up to 60 and 80 feet. I'd say there was a great article or a study performed back in the early 2000s by ADSC that really drilled down on the effects of free falling concrete in drilled shafts. So they installed several shafts. They performed NDT testing, and they verified through the NDT testing, as well as some other methods, that you don't get any segregation or have any detrimental impacts or anomalies to the shafts when free falling concrete up to about 120 feet. That's actually fairly common in Chicago as well. More often than not, you can get a dry hole there, and owners and engineers are typically allowing free fall of over 100 feet. I've personally done over 100 feet and about a 350-yard pour on a big belt shaft in downtown. So I'd encourage people to have an open mind when it comes to free fall of concrete, as well as reading the ADSC article. Second method of installing a shaft is going to be your wet method. And that's going to be either, it's usually utilized when you can't achieve a dry hole. So it's generally done through means of slurry. And this can be utilized with polymer or bentonite slurry, or in the correct conditions, water and maintaining a positive head can be an effective way to drill under fluid. Some of the risks with it are going to be just picking the right slurry. So it's a must to understand the geology you're drilling in, understand how it's going to react and behave under hydrostatic pressure, and understanding how much fluid that it could consume during the course of the actual installation. So the main thing you have to do is with any type of slurry installation is maintaining positive fluid head. This is generally considered to be 5 to 10 feet in conditions where you've got artesian conditions. Then you're going to want to maintain your fluid head greater than 10 feet, sometimes upwards of 20 or 30 feet if you have the ability to do so. Another key part of the slurry installation method is having an operator and tooling that understand the approach. So the idea of the operator drilling the hole, if he comes up too quickly with a full load of slurry, or excuse me, a full load of material on his auger, he's going to actually pull the slurry up with him, which can create a vacuum effect and ultimately heave in the bottom of the shaft that he's drilling. So all the work that you've done by placing slurry and drilling the correct way can be wiped away pretty quickly if you have an operator in the seat that does not understand slurry drilling. Same with the tooling. Generally, if the tooling that's being used should have slurry bypass pipes on it, and that's just simply a way as you're coming up to allow the slurry that's sitting on top of the tool to flow back down below the tool and into the shaft. So this is just a quick little graphic showing a standard installation procedure. So on the left, you see that's a starter casing. Typically, you're going to take the starter casing down into your medium, about 10 to 15 to 20 feet, whatever you think you can get, and then flood that hole with slurry. And then from there, moving from left to right, you start drilling the hole while you are constantly adding slurry to it to maintain your positive head above the existing groundwater table. Then once you set the cage and get prepared to complete the shaft, you're going to utilize a trimming pipe in order to place the concrete. As you're pumping concrete into the hole, you're going to lift the trimming pipe, and the slurry will be displaced out the top of the hole. Normally, this little graphic kind of shows slurry spilling out over the edges of the casing. That's not usually the case. So the appropriate method, usually you're going to have a pump in there to pump it back to some slurry holding tanks. So when considering polymer slurry versus bentonite, as I mentioned previously, you really need to understand the geology. Polymer works very, very well in silts and sands, something that is fairly tight and doesn't allow for fluid escape. Um, Same for non-artesian conditions. The thing with polymer slurry is um, it creates a thin layer cake on the sidewalls of the drilled shaft and doesn't allow for very much fluid loss, but it doesn't have much weight to it. It's roughly the same unit weight of water. So bentonite slurry creates a much thicker layer cake and it has a higher unit weight. So it's primarily used for higher groundwater conditions where you don't have the ability to put 5 or 10 feet of head onto the shaft, or if you've got artesian conditions, or if you have significant gravel layers or even loose sandy gravel layers, bentonite can be utilized because it forms a layer cake on the actual surrounding soil. So you don't see significant fluid loss. Whereas polymer being thinner, if you try to use it in gravel, you're going to see significant fluid loss, fluid takes in the polymer while you're drilling the shaft, which can make it very, very difficult to maintain hydrostatic head. This is really just a couple of good shots of a slurry management system when utilizing polymer slurry. Um, you see on the picture on the left, as the tool is coming out of the hole, there's a pipe that's pumping slurry back into it. That's because every time you make a pass with the tool, you increase the depth of the hole, so the amount of slurry that's in it falls incrementally relative to the groundwater elevation. So you want to constantly be adding slurry back to your shaft as you're drilling it. And normally in years past, before the advent of Venturi mixers, you're mixing all your slurry in your tanks or in tanks. This is still common practice because you really want to get good hydration of your slurry prior to pumping it into the hole. Typically going to utilize about twice to 2.5 times the amount of tanks as it takes to, or as the volume required to install one drilled shaft. And that's because you want to have a spot to pump your polymer back to as you're pouring the shaft, and then refresh the polymer so you can use it in the following shafts. This is just an overview of a bentonite slurry management system. The big difference in a bentonite versus a polymer slurry management system is you've got to utilize desanders. Bentonite tends to hold a lot of sand content, and so when it comes out of the hole, you've got to run it through desander, really clean it well prior to putting it back into a shaft. One of the other major concerns and reasons that bentonite slurry and drilled shafts are utilized less often is because you're often going to see a loss of skin friction when it comes to utilizing bentonite, just because that bentonite leaves a layer cake on the sidewalls of the shaft. So after you've gotten your shaft taken down, whether it's through the process of dry hole drilling, temporary casing, permanent casing, slurry utilization, the next step is going to be setting your rebar cage. So the key to setting a rebar cage is a good pick plan. It's a lot of planning. In this instance, as you can see, the cages are pretty significant. If you see the picture to the right, that's about 150-foot long cage. You look at the picture in the middle, you can imagine it's not very easy to pick a 150-foot long cage and keep it perfectly straight. The idea is to keep it as straight as possible and not to allow it to deform to the point where it bends. And more often than not now, especially in the case of these pictures, these are DOT shafts, so they are going to have CSL testing. So you really need to rig and pick the cage in an appropriate manner that will not allow it to bend so much where it breaks CSL tubes. A big part of that is the cage design. So you really need to design a cage that can be picked. Some allowable bending is fine, but really you need to design a cage that's robust enough to handle the lifting stresses associated with picking and setting. So, as I mentioned, after your cage is set, now you're going to place your concrete. We discussed free fall placement of concrete. Now the wet approach is going to be your trimming placement of concrete. So the key to a successful trimming placement is having a good flowable and workable mix. You're typically going to get a higher slump concrete when it comes to trimming pouring. You're going to target 7 to 9 inches. I always say shoot for 9 inches at batching, and then lowest you want to place at is about 7 inches. You also want a concrete that's going to stay workable. So very often you're going to put in some super plasticizer or in conjunction with retarder, which is in the form of Delvo or another admixture, and that just gives you some increased work time because trimming pouring is inherently much slower than free falling concrete. So you really want to maintain workability. And because it's so much slower, you really want to target a rapid installation as fast as you can. You really don't want interruptions in the placement itself that can result in cold joints in the concrete, inability to maintain head on your trimming pipe because your concrete below is getting stiffer. So it can introduce a whole world of problems if you don't have good concrete and you don't do it quickly and efficiently. One other thing that should be mentioned, you see on this picture on the bottom of the screen with a rebar cage, and it kind of goes back into the commentary of cage design, is you really want to design your tie and your vertical spacing such that concrete will freely flow around it. This is a pretty simple overview of just what a trimming placement from the back chute of a concrete truck looks like. Typical trimming pipes are going to be 10 to 12 inches for larger shafts. Shafts about 5 feet and under. A 4-inch trimming pipe is fine. It's easier to hang that from a pump truck and allows a little more flexibility in placement. Again, just another overview. This is a larger diameter shaft. You can see in the picture on the left, it's got a large hopper, and you're able to back multiple trucks up to the hopper, which is it's great in the sense it allows you to pour much faster. The last few slides here we'll run through are about drilled shaft testing. In this particular slide, what you see there on the left is a sonic caliper. This is utilized to perform a shape test on the shaft. So it's measuring verticality and deviation of the shaft. Typically with drilling, you target about a 1/2 inch, a 0.5% of verticality. The shape test, the sonic caliper can confirm that, but I believe as you see in that small graphic on the right, the shaft looks like it was deviated a little bit further out than that 0.5%. The next more common method of NDT testing is what's referred to as mini-SID testing, and this is just a camera. Mini-SID is the style of camera that's being used. And in this approach, you drop this cylindrical camera housing system to the bottom of the shaft. And it has a little needle. It can measure visually the depth of sediment that's on the bottom of the shaft. And then it gives you a good visual view of what the bottom of the shaft looks like. You can't see the sidewalls of the shaft utilizing a mini SID, but you can confirm bottom of the shaft cleanliness. And this is especially common and necessary when you've got an in-bearing shaft. The next, and is becoming more and more common in the industry, is squig testing. This is a method that was developed by PDI, which is Pile Dynamics Inc. And it's a shaft quantitative inspection device, as the name acronym SQUID alludes to. It's a great method for going down and testing the bearing stratum of a rock socket or of a drilled shaft when in bearing is critical in the design. It has these 3 little feet on the bottom of it. You can lower it down with the drill rig and move it around to several different areas of the shaft bottom to physically test the bearing capacity. After your shaft is poured, the two common NDT testing methods utilized these days are CSL testing and tip testing. CSL testing is what you see in these 2-inch steel tubes in the shaft. And all this is cross-hole sonic testing. So you're installing probes down each one, kind of in a back and forth fashion. And it's utilizing ultrasonic waves and frequency to measure the quality of the concrete across the shaft and give a shaft profile. Tip testing would be what these yellow wires are. And what tip testing is thermal integrity profiling. And that's going to measure actively the heat of hydration of the concrete to determine whether there's a shaft defect, if you've got uniform concrete placement in the shaft or not. And the last one is the big one. It's load testing. Typically, load testing for drilled shafts are going to come in the form of an O cell, which is an Osterberg cell. It's a bidirectional load test. The load cell or load cells are tied into the rebar cage. And after the shaft is completed, it has hydraulic controls that extend down to the O cell itself, as well as telltale wires. And it physically tests the capacity laterally and in tension of the drilled shaft. They can be utilized for reducing shaft diameters or shaft lengths, where the contractor tries to implement a value engineering approach and prove out their design. Bidirectional testing capacities usually are from about 200 to 6,000 kips. And like I said, they're very expensive to perform, but in the long run, if you prove out capacity of a shaft through a load test, you can ultimately streamline design and save the owner some money at the end of the day. I'm going to kick it over to my colleague, Ryan Getz. He's going to give you a case study here on Sulaks. Thanks.
Thanks, Tyler. Ryan, you're muted, buddy.
There we go.
Hear
Thanks,
you loud and
everybody. We'll go over a small case study here in the short time that we have left. I will say that when we do this presentation, sometimes we do get into secant piles. A lot of the techniques we just talked about there with Tyler can be utilized for secant piles, which in essence is overlapping drilled shafts. So we've excluded that from this presentation today. But if that is a webinar you would like to see in the future, feel free to put a note there in the chat so our team knows to put that on the schedule for the future, and kind of a drilled shaft 2.0 getting into secants. So our case study we're going to talk about today is at Sioux Lock, more specifically third lock at the Sioux, phase 3. This was with the Cozine Alberici trailer tri-venture. And we're kind of calling this specialized drilled shafts. This is maybe a little bit unique. Depending what your background in drilled shafts is, you may find different things interesting, whether that's diameter, depth, rock, installation technique. So we chose this job just due to kind of some installation techniques and kind of some irregular equipment than what is typical in our minds. So I will say that a lot of the images used here are from the U.S. Army Corps of Engineers, Detroit District. This is their project in northern Michigan. So this is at Sault Ste. Marie, which is at the very end of Lake Superior, as it empties kind of into Lake Michigan and Lake Huron. This is very important for the nation, for our iron ore supply chain. A lot of that stuff is coming from northern Minnesota Iron Range, coming through the Sioux Locks and then going down into northern Indiana, Detroit area, northern Ohio. And, you know, this lock is also critical for, you know, just other commerce going into northern Michigan and Minnesota. You know, on a given day, you see numerous very large vessels going through this lock. So the point was to provide some redundancy and increase the lock size. This is a rendering here. So Canada is going to be on the left side of the page. The United States, Michigan, is on the right side of the page. To the right side, the Poe lock, MacArthur lock are two locks that are being kept. On the right side here, this is where the Davis lock and the Sabin lock were. The purpose of this project overall is to decommission those two locks and replace the Sabin lock with the new lock, the new third lock. This lock is going to be the same size and shape of the Poe lock, which basically builds a redundancy in the system if one of the locks has to go down for any sort of maintenance in the future. This is a overview of the site. This was taken from last summer, so there has been some work in the last year that has gone on. But in the bottom here, you can see the existing Davis lock. This is all being infilled here. A little bit above that, you can see the new monoliths starting to be excavated more on the left side of the page. And then as you get right, they are being built up. It's going to be the new walls. And our work is going to focus up here to the top of the page to kind of this more gray-white area is what's called the MPP bridge. So the purpose of this is to provide access for people, equipment, and utilities from existing infrastructure kind of in the middle of the river there to the new lock. If we're looking at, scope of the shafts, not a huge quantity or size, but we'll get into the kind of the complications here. There's 20 each rock socketed drill shafts. They utilized a 40-inch casing and then continued with a 36-inch rock socket. All these shafts were CSL tested. And then we utilized our sister company, Birminghammer, out of Hamilton, Ontario, Canada area, their equipment manufacturer. So we utilized them. And we also worked with our sister company, Solotanjbashi Canada, in some of the execution of this work. This is kind of a layout of where those shafts lay out. We have 3 to the south on land. In general, those are relatively easy. We have 4 on embankment to the north. These start to become more complicated. All the red area, you cannot load, you cannot put equipment or do anything there. This area is a slope one, and then it's covered with a bunch of old fill. This is not simply just a few, riprap rocks on top that you can scrape off and then get to good material. This is stuff that's deep, continuous, been there a long time. And then we have some shafts over in water, but as you can see, those are still even on the very side of the riprap. When they were installing this structure here in the river, there was some different rock excavation that's been done. So the rock levels greatly vary through here. So this becomes a little bit more challenging. And then additionally, a crane barge does not fit in this area, so we have to get some extended reach. So when we looked at this job, we said, okay, we have to have reach. What can we do? We're probably going to need some sort of a crane attachment. Tyler had mentioned some conventional crane attachments that use your core barrels, augers, those sort of things, but they're limited to 35, 40, maybe 45-foot range. Due to the crane barge not fitting in here, we need to sit back more towards these blues. We simply didn't have the reach. So with that, as mentioned, we worked with our sister company, Birmingham Foundations, and we kind of came up with a lead system. Leads maybe more traditionally you've seen with driven piles, auger cast piles. But as Tyler mentioned, we can work these on shafts. So for this job, real quickly, we used a semi-fixed configuration that you see there, as well as a flying configuration when we needed to reach those really far out shafts. Also, we used here reverse circulation. Tyler briefly mentioned this. So we use reverse circulation with a ring bit casing advancement system. There's a few different manufacturers types here, but in general, you'll see on this photo to the left, we put a ring bit is welded to the bottom of the casing, has little kind of bullet teeth or carbides on the bottom, and then you'll see these joints here. We go to the center picture and we see our down the hole hammer here is in blue, and then the bit at the bottom, and you'll see that there are some locking mechanisms on this full face bit. So this bit actually locks into the casing, and as that hammer vibrates up and down, it is actually driving the casing, advancing the casing with it. We chose this system to advance the casing because of that riprap fill that we see in a lot of areas. You can't conventionally just drive casing, for example. You can't just use your auger to try to get those large rocks out. We felt this was the best way to get our casing that was required into the ground, as well as then continuing on. You can unlock this bit and you can continue on and drill out your rock socket. This is kind of what it looks like on the lead system without the casing. The spoils in general come from the bottom, will come up the side here. There's a couple ports in the drill string. Using, in essence, suction, it gets sucked up the drill string, comes out, and then you can see a discharge hose over here on the side that the spoils would go out to a waste barge. This is what it kind of looked like from the air, and you can see that our little 20 shaft job becomes rather complicated really fast. We have a kind of a support barge here in the channel with some man lift support equipment. Here in kind of the center of the picture, you can see the crane reaching out to do some of these water shafts. You can see a variety of templates being utilized in the water to make sure that these shafts go in the correct location. On reverse circulation, the other thing is we are using air. So you can see 4 air compressors that were required for this job that need to be on the barge as well. That is a pretty quick overview there of something different. So I'm going to leave it at that, and Brian will join us again, and we'll try to answer, I think, a few questions here before we run out of time.
Yeah, thanks, Ryan. Appreciate that. Great job, and thanks to Tyler and Frederick for your help and the information you shared throughout this last hour. We do have a few minutes, so we'll try to address. We can't get to all of them. There's just too many for the time we have remaining, and we want to make sure we're aware of time. So we will answer a couple questions, and the first we'll talk about. Maybe Ryan, you can help Tyler, maybe if you're still on, about the main difference. One of the questions was more about the technique. The main difference really between vibratory installation and oscillating.
Yeah. So with an oscillator, you're twisting. You're using hydraulics to twist, rotate the casing into the ground. Is a non-vibration type method. With a vibrator, you are using a high frequency, usually clamping onto the top of the casing, using that high frequency vibrator to actually vibrate the steel over your full depth to be able to advance that casing. So it's more of a twisting versus vibrating.
Yeah, and maybe there's a couple questions around geotechnical investigation and where we would suggest, or one may suggest, a scenario of doing a pilot boring per every drilled shaft location. I think definitely in structures like bridges where there's monopiles, things like that, where there is no redundancy, we're seeing obviously the recommendation that there must be a boring at every single location. But any other Any other suggestions? Maybe Rye, I think you had highlighted some stuff in your answer to one of the questions before.
Yep. Yeah, I mean, I think it's a good question. I think when you work with a lot of rails, specific DOTs, they are requiring that boring at every shaft. Where you do have permanent casing, it is helpful, especially if that boring is done in advance, because you can order your right length permanent casing. That's an expensive material. So if we can get the right length there from day one, that's great. I think it just really depends, kind of what your geology is too. And one of my other questions in a karst geology, especially if you have pinnacled rock, the more data points you have, the better. Obviously, it depends how many shafts you have on your job. If you have 400 shafts, maybe that's not totally reasonable. If you have 20, maybe it is worth doing the borings. If you have a pretty level, reasonable geology that's pretty uniform on a small site, a grid of borings is probably sufficient. But it definitely does add to the overall risk of the project, the fewer borings and the less information we have. So the more is better.
Yeah. And there's another question about, a lot of the testing methods that we discussed, and we'll stop it at this one. A lot of the testing methods that we discussed, like CSL, OCell, or generally post-construction, right? You've already installed a shaft, a test shaft or production shaft, and there's a requirement for obviously investigating your capacities, bond stresses with the OCell, your design parameters, as well as the CSL, and maybe an anomaly or requirement per the specification to do a CSL test on a certain percentage of shafts. But the question really came in around, anything that we are seeing in addition to maybe our general QA/QC procedures for in real-time installation during construction testing. Maybe anything you're seeing there, Rod, just reiterating things that we're doing.
Yeah, I think once again, sort of comes down to the specification. Comes down to the type of the shaft you're drilling. If you're doing for a one-story non-critical structure, your requirements may be different than a 10-foot diameter shaft for a monoshaft foundation, right? So I think with all this testing and stuff, you just got to really put in perspective what your structure is, what's the criticality of your structure, what's the redundancy of your structure there. I guess I'll start off by saying that.
Yeah.
I think, when you get to rock sockets, the downhole inspection devices are becoming relatively more common, even on building shafts with higher capacities. We are seeing more CSL testing and tip testing on those shafts. There are cameras required on some jobs. I just caution people with cameras and what you can actually see, especially if they're wet holes and just how well those really
Exactly.
work.
There's a lot also of information coming from the drill itself.
No, that is true. There's a lot of
more and
information.
more data coming from the drills.
Yes.
So you have more data from that.
No, that's a great point.
I think we're at the top of the hour, Brian.
We are, yes. Thank you. We are at the top of the hour again. Everyone, thanks. We crushed our latest record of amount of visitors that have sat in on a webinar for us. This is our highest rated or our highest participated webinar. So again, thank you very much. There was a question around what we can share. We typically don't share the slides. We will send out the PDH and the answers to the questions. And I think we usually send out a recording of the webinar itself. So we will definitely make sure that those get to you. There is no survey at the end of this, but you have been providing some ideas. Should you have any other further ideas, please let us know. Send us a message, hit me up on LinkedIn, whatever you want to do. And if you do not follow us on LinkedIn, please go find Nicholson Construction, because we do post our future webinars there. And since you have participated today, you will automatically be added into the list for notifications of future ones to come. So again, thank you very much, Rye. Tyler, thank you. Frederick, thank you very much for standing in for Andy, who hung you out there. So again, great job, guys, and great questions and great participation, everyone. Thanks again. We'll see you soon.
Thank you. Thank you. Thank you, Brian. Thank you, Brian. Thank you, Tyler. All right. I'm stopping the record. Thank you, guys. I think we can just log off.
All right, then. Thanks, Frederick.
I'll talk